Good afternoon. I would like to start by thanking the organizers for giving me this opportunity to present my ongoing work. Today I'll tell you about bacterial carpet and their interesting dynamics. So let me start by explaining what a bacterial carpet is. So we have these flagellated bacteria and we take, which they rotate and generate flows. We take these type of bacteria and attach their head to the surface, and now if we put many of them together, we will have a bacterial carpet. This is an experimental demonstration of a bacterial carpet where we have thousands of these flagellated bacteria attached on the surface and they are trying to generate flows, and indeed their coordinated activity gives rise to these large scale flows. These people study this by putting some tracer particles near the surface of the carpet and far from the carpet, and what they found is an enhanced diffusion in these tracer particles. And if we take a isolated patch of such bacteria, a bacterial carpet, which is free to move, you can see it spontaneously start rotating because of the flows that this bacterial carpet is generating. So from experiments, we know that there are large scale flows generated by this bacterial carpet, and also there is actively stirring in the surrounding fluid by this bacterial carpet. Our interest here is to make a theoretical model for this bacterial carpet, and we are also interested in studying their collective dynamics, transport properties, and what type of different flow profile we can obtain by taking different density pattern of this bacterial carpet. Before going to full model, let me tell you some important things about single bacterium. First, consider a single bacterium. So in the bulk, it is a force-free and torque-free particle, given that there is no external force or torque acting on it, and it propels by rotating its flagella, which pushes the surrounding fluid, and in response this moves forward. So this swimming mechanism gives rise to a force dipole, and because its flagella is rotating in one direction, to conserve total angular momentum, the head has to rotate in another direction. So this gives rise to a torque dipole. But the far field signature is that of a force dipole, and this has been verified in experiments also. So it is not only a theoretical prediction, but in experiments also it matches very well. Now, if we take such bacterium and attach its head to the surface, so now its motion is constrained, the head can no longer translate or rotate, so the effective description will be reduced to a force monopole and a torque monopole. This is our basic building block for the bacterial carpet, and what we want to model these type of particles now, which are attached to the surface. To model this, we can think the flagella or backbone as a rigid rod attached to the surface with orientation vector p, and when there is no perturbation of flow, this prefers to stay normal to the surface, and given any slight perturbation, the toroidal spring will give some effects. So it's like any small perturbation will try to disalign it, but there is a toroidal spring which will try to bring it back. So this is how we are going to model it. And now let's look at the full model. So we divide our domain in two regions. One is active region, another is passive region. And we are working in low Reynolds regime, where the governing equations are that of Stokes equation. For the active region, we have this momentum balance equation for the fluid UA and pressure QA, but with forcing terms coming from the bacterial carpet activity. This force density F corresponds to the force monopoles, and the contribution from torque monopoles is entering through this antisymmetric stress. For the passive region, this fluid obeys the standard Stokes equation without any forcing term like this. And at the interface of this active and passive region, we have these boundary conditions. So we are also imposing no slip boundary condition at the base surface, and at the interface, we impose this continuity for the velocity as well as the direction matching condition. So these equations sets up the problem for the fluid. Now we had this bacteria with orientation vector p. You can see here these. For that, we have one evolution equation for their polarity, how they are going to evolve. So it has two terms. First term tells how the orientation is going to change if there is a local velocity gradient, and second term comes from the restoring torque, which tells like in which direction it will try to align given any perturbation. I'm not going into very detail, but one can systematically obtain these all equations starting from microscopics and using different tools like slender body theory and other. You can also notice that there is a passive bit coming from this restoring torque entering in this force density here also. And at the end, the full system is described by this set of parameters, only a few parameters, where this rho bar is the mean density, basically how many particles are attached on the surface per unit area, and the other relating the activity of the carpet. Now, since I have given you a brief idea how we are modeling this system, let me show you some of the results. So we start by linear stability analysis. We start with the state where all the bacteria are aligned in z direction. Then there is no mean field flow. So this is what we are calling base state. Then we are introducing a small perturbation in the plane wave form characterized by the wave vector k. And once we linearized all the governing equations, we solve for the eigenvalue of this system. What we found is this. The real part of the lambda is positive, indicating that there is a positive growth of the perturbation. But at the same time, there is non-zero imaginary part of the lambda, which signifies that there is oscillatory behavior also in the system. And also you can notice that k equal to 0 is the fastest growing mode, indicating that there is a long wavelength instability in the system. Now we ask what happens in the full nonlinear simulation. To do that, we start with a uniform carpet and introduce a small perturbation. And you can see with time the system settles to a oscillatory state. So all of them aligned in one direction, and they start rotating together. Because the emergent state is quite simple, let me play this movie again. We also try to understand this analytically. To do so, we start with the state that all of them are aligned together at some angle with orientation vector p. So let's say at some theta and some phi. And using our governing equations, we use what type of flow they are going to generate and to study how this theta and phi are going to evolve for this state. What we found is that theta dot is constant. So all of them are kind of rotating with a constant angular velocity. But phi dot has some phi dependence. And what we found is after some variation of these controlling parameters, after some cutoff, we will get this pitchfork bifurcation. So indeed, these are same case that we observed in the nonlinear simulation also. So the system makes a transition to this aligned state and then starts precessing together. Till now, all the results are for uniform carpet. Now we ask, what if we put a density with some heterogeneity on the carpet? To do so, we start with these two models of density field. One is Gaussian patch, another is elongated. And the corresponding polarity evolution for these two fields looks like this. So in the Gaussian patch, you can see the system reaches to a steady state. All of them, the polarity vector get aligned in some swirling pattern. But for the elongated Gaussian case, the system reaches first to a metastable state. And you will notice that it makes a transition to a stable state. It's a little slow. Let's just do it. And then it will reach to a steady state where all of them will get aligned and start rotating, which is kind of similar to the earlier case, but there is a phase difference in all of their orientation vectors, and whose importance we will see in the flow profile, which is still under construction. So I would like to end here with this photo of people that you all know looking at a spinning object, and hopefully you understand that study of spinning objects is quite interesting.